was just precompiled Forth words. And as we're going to see, everything you do in Forth is a word. That's basically the commands of the language. And you define new ones to do new things. And the way Fig4th was implemented, most of it was just ordinary Forth precompiled code. Somewhere along the line, a group got together to create a real standard of it. They created Forth 79. A little bit later, they created Forth 83. Around 94, ANSI jumps in, creates their standard version of Forth that's normally called ANS Forth. And I have seen there is a website of some organization that is dating their attempt at trying to create a new standard at 2015. I have no idea how big this movement is, who they are, or what they're trying to accomplish. But there is apparently still enough interest out there that there's a group trying to update the standard. The other interesting thing is because it's such a small, simple language, it's easy to build CPUs that like it. Some CPUs, you just kind of look at the machine design and think, they must have been thinking about Forth when they created this. I think that every time I look at the 6809. I had a friend in college who, for his senior project, built a little CPU. And he oriented, basically was a stack CPU, oriented around a subset of Forth. These are some of the various machines that have been built over the years that run essentially some form of Forth as their machine instructions. The Harris and Novix are probably the best known of the early ones, though they're not available anymore. The GA 144 is the latest thing that Charles Moore himself is now making available. He's got a company called Green Arrays, and they're building these highly parallel chips, and each core on the chip is running Forth. The 144 in that name is how many cores are on that chip. It's a 144 core chip that's running Forth on every core. So you can imagine, if it's such a small, simple language, then it would make a very small processor. You pack a lot of them onto a chip. Okay. How many of you have ever been frustrated by trying to figure out where the parentheses and the braces and the semicolons and the colons and whatever symbols are in a language? The beauty of it is Forth has no syntax to learn. The only thing you have to understand is that you separate the words by spaces. That's it. That's the only syntax you have to know for the language. Which makes it a beautifully easy language to learn.
At least easy language to parse.
Yes, which is also part of how you end up with such a small interpreter. Now, the other thing about it is that it's all oriented around a data structure called a stack. Now, how many of you are familiar with the data structure stack? Most of them, good. Essentially, it's defined by pushing and popping. That is, we always access the top of it. So if I'm going to add something to this data structure, it goes onto the top and obscures whatever was underneath it. If I'm going to take something out of the structure, I'm popping it by always retrieving the thing that's on the top. The best analogy, or the best sort of quote-unquote real-world picture, I think, are these cafeteria plate dispensers. You always take the plate off the top and then you put plates on top. And you have this spring-loaded thing that the plates just go down. And that's what we're going to be working with in Forth. Everything happens on the stack. The terminology, by the way, you will hear this last in, first out structure. That comes from accounting terminology. What accountants have to do with stacks, I don't know. But they has to do with how you expense things. Okay, so now that we've talked a little bit about what the language is, let's start actually looking at some of it. The first thing to know is that if the word is a number, then it just gets pushed onto the stack. So while I may say, oh, I'm going to do something with the number 3, what I'm really saying to the Forth infrastructure is push 3 onto the stack. Now, in this first example, it's followed by a dot. Now, what the dot means is, take the thing on the top of the stack and print it out. So, this first line right here is basically print 3. The next line puts 3 under the stack, puts 5 under the stack, and then prints. So what are we going to actually get printed out here? 5, because that's the thing on the top. We're processing it left to right, so the 3 goes on first, then the 5, then we're going to print the top of the stack, which is the 5. Well, so the third line probably is not terribly surprising. 3 and 5, add them and print out the result. And then we've got the exclusive OR here to do bitwise operations. Now I'm going to go ahead and illustrate this on a fourth implementation here. This is the Fig fourth that I had talked about earlier. This is the version running on a 6809 processor on this little board right here, which is just a little homebrew single board computer that, well, okay, the story behind it basically is I was bored one weekend. It's like, I want some kind of a little thing just for fun that's not serious. I'd never worked with the 6809. I'd always liked the look of it. I'll do a paper design of the 6809. Let me try some of this schematic capture software. Oh, that looks nice. Oh, can export to a board layout. Well, by that point, I didn't have any choice. I had to get the board made and build it. This is actually the second version of it. Yeah.
Do you sell them?
No, I don't sell them, but I do have all the design information online. So anybody's free to take them. I did look at possibly running up a bunch, and at least the few people I talked to at the time didn't show much interest. But of course, I did the usual sorts of things. Instead of a floppy, I've got a SD card. I couldn't find any 64K chips, so I dropped in a 128K chip, which meant I had to design me a little memory management unit because I wasn't going to waste half my memory. But it was sort of the, okay, what would have been for me my ideal computer when I went to college? And that's how this thing kind of ended up where it is. So anyway, it's running the Fig fourth implementation right here. So if we look at, for example, at the next to last one that we just showed on the slide, where I'm going to push 3 and 5 on the stack, add them and print, well, not too surprisingly, I get 8. And as we'll see a little bit later, I could actually print that in any base I want, up to base 36. Well, if you go beyond that, it gets kind of hard to keep track of. But the fourth doesn't care. So the other one that I showed there, the exclusive OR, this does the bitwise exclusive OR. So 3 and 5, if you think about them in binary, exclusive OR to bits, you get 6. So you've got not only your normal arithmetic, but you've also got bitwise Boolean operations available to you. Unlike most languages, the minus sign is only used for binary subtraction. If you want unary negation, you have a separate word called minus for that. We also have mod and abs, the sort of usual remainder absolute value. There's a variant that is /mod available in most versions that will give you both the quotient and the remainder if you want them. There are double precision versions of many of these as well. But this gives you kind of the basic flavor of the fundamental operations you can perform in the language. And as you saw, you can do it interactively. You don't have to write a program. You can just operate interactively the same way you could in BASIC or a lot of these other sorts of languages. Now the other thing we want to do with the stack is actually manipulate the stack itself.
This is fourth.
Yes, this is fourth. And you're coming in just as we're getting into the stack manipulations. So this is the right time to learn about fourth because it's called stacks. Now obviously if we've got numbers that we can push onto the stack, we know at least some ways of popping them off by operating on them, but we might need to rearrange things on the stack in some way. Sometimes we need a number duplicated. That comes in real handy if I'm going to say perform a test on the number which will eat up the value on the stack, but I still want the number there to do something with later. So that dupe duplicates the top of the stack and gives me 2 copies of the same thing. Drop is just a pop, just throws it away. That's useful if I've been keeping this thing around because I think I'm going to need it later and I finally decide I don't need it anymore. There it goes. Swap, kind of as the name suggests, just takes the top 2 elements of the stack and flips them. Rotate is a little bit more interesting. It takes the 3rd element of the stack and pulls it out so that the other 2 drop down and it puts the 3rd back on top. That one's probably best illustrated. So let's put 1, 2, and 3 on the stack. 3 now is at the top, 2 is at the middle, and 1 is at the bottom. Now if I do a rotate, now I'll print the 3 out. So I'm getting out 1, 3, and 2 because what's happened is the first one, the lowest one on the stack, has been pulled out, moved to the top, and then the other 2 shifted down. So rotate operates on the top 3 elements and just essentially creates a cycle of them. That turns out to be handy, among other things, if I'm operating on like 3 vectors, XYZ vectors or whatever, and I want to do something to all 3 values. I can just cycle through them and do something to the top each time. And we've got an example where I will actually do something like that. Over is a little bit more interesting as well. We'll put 1 and 2 on the stack and do an over. And now what happens is I get 1, 2, and 1. Over copies the second thing on the stack over the first. And now you've got 3 things on the stack. These last 2 operations, they are essentially how you can do what you're not supposed to do with stacks. You can actually go and touch memory. If you really insist on having variables, you can have them, and this lets you retrieve the contents of a variable or store it into a variable. So the exclamation point is pronounced store, and the @ is pronounced fetch. And so these are how you go about talking to memory locations. Obviously, if you're also working in a control environment like Forth was originally created for, that's how you're going to talk to the ports that turn motors on and off and that sort of thing. Okay, I said we can operate in any base. Typically, at least 2 of them are going to be kind of predefined in the language, decimal and hex. A lot of implementations will also give you an octal. But I can set it to any base I want by storing it into the variable called base. Now, the way variables work is, just like everything else, it's a word. When you execute the word that is a variable, what it does is it puts the variable's address on the stack. And then you can use the exclamation point to store or the @ sign to retrieve. So let's say I want to know what base I'm currently in. Well, I will put the address of base on the stack, fetch its value and print it out. Well, of course, whatever base I'm in, that base is going to be printed as 1, 0. So, I can go over here and change this to hex and say, all right, well, base at the high. So get 10. Well, if I wanted to actually do this and say what base was it, I could say base at. Now change into decimal and then print it. And then we were at 16. Of course, I've changed it to 10 now. You can make any base you want. So for example, if we were to go to base 5, and then we were to try that thing that we did before where we add 3 and 5. Oops. You can't add 3 and 5 in base 5. So we'll add 3 and 4 in base 5. And we get 1, 2 in base 5. You're not restricted to base 16. You can go to higher bases. So let's take some big numbers and then we'll go to base 24 for fun.
I'm gonna have trouble with that,
There's a 5.
Oh yeah, I'm still in base 5, aren't I? Well, we can take care of that. All right, so put in a big number, switch to base 24, and print out the number. And you can see it printed out as LA9. What it does for bases beyond 10 is it just uses the letters of the alphabet, A, B, C, D. So, just like we would for hex normally, the A through F would be 10 through 15. If you're going beyond that, it just keeps using the letters of the alphabet. That's easily handles up to base 36. Once you get beyond base 36, it just keeps using the characters in the ASCII character set. So you can get things like square brackets and other sorts of things. And then eventually you'll get to the lowercase letters. Now the other thing that's a bit of an issue is it doesn't really want you to input values in these large bases, because if it's a base 36, how could it tell the difference between, well, yeah, base as the name of a variable and base as a value. So there's a little bit of a limit to what can be practically done, but it is kind of an interesting example of what you can do in the language. So, as I said, the way that works is, if I'm going to store something, I need the value I'm going to store, the address, and then the exclamation point just modifies that value. So what you do is you put value, variable, exclamation point, and that would make the equivalent of an assignment in most languages. Okay, now things get interesting, because we want to be able to define new words. Now, most of the time what we're interested in is defining something that does some kind of an action. Essentially what we would think of as procedures or functions from other languages. And you do that in Forth with the colon. The colon is the word that says begin a definition of a new word. In particular, this is a new word which is going to exist as a command. It can be used by other words. And we terminate it with a semicolon. So, unlike other languages, in Forth, the only place you have to remember to put the semicolon is at the end of a definition. That's it. You can create other words. For example, there is a word called variable that is used to create new variables. So if I were to say variable temp, like we have here in this example, that would reserve a memory location, give it the name temp, just like any other variable declaration does. And now I can use it in the same way I use variables like base. That is, if I execute the word temp, it puts the address of that variable onto the stack. I can either retrieve or store to it. Yeah.
All variables are global?
Yes. It doesn't really have a concept of scope. Now, it is possible in some versions of Forth to maintain what are called vocabularies. And in the context of vocabularies, you could say, all right, I'm going to load this particular vocabulary. It will give me names that know about each other, and then I can discard that one and bring in a different
It's
vocabulary.
like a namespace.
You could, yeah, you have a little bit of capability like that, but not really quite the same as, say, C++ namespaces. Yeah.
I don't want to jump too far ahead, but with your earlier point, you want to have side effects that are specific memory locations.
Mhm.
It sounds like variable by itself will define some memory location in
Right.
RAM. How do you actually set it to a specific location?
There you would want to use constant.
Constant?
Yeah, so if I define constant to be a particular memory location, so let's say I'm looking in the documentation, the data sheet on the chip, and it says that a particular register is address, A104. Well, I would go into hex, define the constant A104 with whatever name I want to give it, and now, whenever I execute the constant word, it puts the value onto the stack, which in this case happens to also be an address. So that's how you would use that to essentially create a label for a memory location that you have predefined what you want to do with it. And if you ever want to know what names you got, there is the command vlist. Now that's not present on every implementation of Forth, but most of them have something like it. And here are the words that are part of the default set kind of when you start up Fig Forth. You've got all of these different words. Some of them are variables, like base, right here. Most of them do something interesting. You've got things like increment and decrement. I, J, and K are kind of interesting. I'll talk about them in a little bit. You've got some interesting stuff. The parenthesis, that starts a comment. But remember, all words have to be separated by spaces. So you can't go parent something. You guys go parent space something to be a comment. Let's see. Oh, the square brackets, that's also kind of interesting. If you're in the middle of defining a word in one of those colon definitions, and you want to sort of break out of the definition process and execute some code right now, you can put it in square brackets. It's square bracket space, whatever you want to do, close square bracket, and then that returns you back to the compiling operation. Yeah.
Why are the numbers 3 to 0 there?
That really is to speed things up a little bit. In other words, it recognizes these as commands and doesn't process them using the normal number parsing. Instead it says, oh, that immediately takes me to a routine that pushes that value in the stack. It's a little bit of just a speed boost is the only reason it's there. And honestly, I'm not sure how much it really buys you. But it has been somewhat traditional in most Forth implementations to have the first few integer values done that way. Let's see.
So
Anything else?
conveniently, you can define like 7 to return 3.
True. Very much like the old Fortrans.
Yeah.
If you're familiar with very old Fortran, everything was passed by reference, including constants. So there is a question in the hacker's test, have you changed the value of 2? And what it's referring to is, in these old Fortran compilers, if I pass 2 as a parameter to a function, and that function changes its argument, the way a lot of these were implemented, it reserved a memory location, put a 2 in there, and used that as the pass by reference. Well, if you change it, now every other occurrence of 2 suddenly becomes whatever you changed it to. So yes, you could in principle do that here. You could define a word 7 that pushes the value 4 onto the stack. So if you really want to do obfuscated code, Forth gives you all the machinery you need.
I don't know, I thought Forth was pretty obfuscated even when you didn't try it.
Yes, it's kind of one of those things that the languages I like best seem to be the ones that most people find very difficult to understand. As I mentioned at the beginning, Forth and Lisp are 2 of my favorites. I haven't really learned APL, but I feel like I need to. One of my roommates in college was a big APL guy. He made a bet with his professor that if he could write a 1-line date and time program in APL, he'd get an A in the class. He did.
You could create
Yeah.
you could create an Enigma program that scrambles.
There you go. Yes, we'll do encrypted Forth. I haven't actually written an Enigma simulator in Forth. I should do that sometime. I wrote one in Go not too long ago. I haven't written one in Forth. Okay. What else? Okay, well, let's look at this example right here. Here we're defining a function or a new word, and whatever string you put after the colon is the name of that new word you're doing. Same sort of thing happens with variable and constant. The string that follows that command is what will be the name of the thing you're creating. So here we're going to create a function or a word called SQ for squaring, and, well, it'll simply be duplicate the top of the stack and multiply. Pretty straightforward conceptually, and it operates pretty much as you might expect. I'll say colon execute dupe star. And then let's say 42 square and print 1764 is apparently what 42 squared is. If anyone wants to verify that, feel free. I think I'm still in decimal. Maybe another base, who knows? So that's the basics of how you would write code in Forth. You just define words, and then you use your words later in other definitions. In other words, it creates a sort of ethos around which you're doing everything in terms of these very small little definitions of things. Some people even go so far as to say, if your definition takes more than one line, it's too long. The sort of model and the value system of the Forth world is lots of very, very small functions. And then you build on top of them. Another way of looking at it is that people will tend to create their own language that is specific to the application at hand, and then write the solution in this application-specific language, where you're defining these words to be that language you want. And if you really want to get deep into it, you can even go about defining new words that have the sort of effects that the colon word or the variable word or the constant word have, that go off and actually allocate space, put new words on into the vocabulary and so on. I won't get into that part. But if you want to get really deep into the language, you can do that.
So you're extending the language as you're
Right.
going along.
And that's one of the nice things about it. Very much like Lisp, there's no real distinction between the inbuilt mechanisms and the mechanisms you define. They syntactically are used in the same way. So you really don't see a difference between the things that you've defined and the things that are defined for you to start with. And personally, I think that's one of the things that is particularly elegant about languages like this. I can't in C define a new type of loop structure. I only have for, while, and do. That's all I've got to choose from. But here, I could do that if I wanted to. Okay, so as long as we're talking about such things, let's get into the control flow. Now, this is one of those things where anybody who comes upon Forth immediately goes, wait a minute, this is a little weird. Because in Forth, it's not if then else, it's if else then. Remember, everything's operating on the stack. So what happens is the keyword if looks at the top of the stack, pops the value off and says, was this 0 or not? In other words, was it false or true? 0 being false, anything else being true. Now, if it's true, then the code following the if is executed. If it's false, then the code following the else is executed. So, the else plays the same role that it does in other languages. It separates the true branch from the false branch. But the fact that there's an if at the beginning instead of an if-then at the beginning, and then you've got a then at the end to wrap the whole thing up, some people find that a little on the confusing side. I don't know, just a fun quirk of the language, I think. Do loop is your basic simple loop that just increments by 1 each time. If you want to increment by something other than 1 each time, you can do this plus loop version of it, where whatever you have here is added to the index of the loop. Now, notice I haven't defined an index name here. That's because it's always called I. I is a built-in word that says, fetch the current loop index and put it under the top of the stack. A little bit different than we're used to in most languages, but it turns out to be very simple to use and very straightforward.
So you can't do nested loops?
You can, but if you want to get at the indices of the others, Well, you've got a couple of possibilities. Some fourths, like this one, also define for you J and K.
Oh,
If you don't have that, you can put it onto the stack before you enter the inner loop. And now you've got the outer loop's index available to you for use later. It's just kind of whichever one fits the fourth you're using.
But those words are defined in terms of, so how would you define J if there's a conventional way of doing it? And
Well, what you would tend to do is instead of defining, well,
Well, they're not variables.
yeah, they're not variables.
so they must be on the stack.
Well, they push a value onto the stack. But what they push onto the stack, unlike a variable, which pushes its address onto the stack, these push the value onto the stack.
What's to get that value?
And that value is something that's internally held without a name, in effect. Unlike languages that we're used to where you name your index variables, here the index variables are kept anonymously, and you can reference the innermost one with I.
So the active index label, is that just dependent on your nesting level, or?
Yes,
Okay.
exactly.
And if you need to do it more than 3 deep, you're doing it wrong? Is that, I mean,
Probably,
seriously?
yeah. Actually, that would be a valid answer for a lot of folks in the fourth world. The idea being, if you're doing it that deeply, you really should have an inner loop being its own function, and then that
Exactly,
word
yeah.
called within.
Is this function definition destroyed, or can you actually retrieve the, for example, a dupe star?
In this version, you cannot. There are versions which, normally they don't keep the text of it, but what it'll do is it'll go back and look at the code that was compiled and decompile it and show you what was there. Because the way this gets compiled, in Figforth especially, and in many instances, you really just build a list of addresses of subroutines. And so when I go to execute SQ, what I do is I sit there and say, all right, I've got a sequence of 2 operations, the address of the dupe code, the address of the star code, I'll hit those 2, and then I'm done, return. There are variations of the language where what gets compiled is actually real jump to subroutine calls. Those obviously tend to run a little bit faster, but then they take up a little bit more memory. There are a few things that will go and say, well, all right, some of these things like the add, for example, the plus. What I'll do is I'll treat that as a macro. I'll copy the instruction code in. And then for more complicated ones, I'll put a subroutine call in. And that gets you about as fast as you can get with it. And it does tend to be a fairly fast language because there's so little overhead for it to manage.
So as you're building this dictionary of words, at what point can you just say, like, freeze and shut down?
Well, this version of Forth doesn't really give you a way to say, take a snapshot of my current vocabulary, store it off to the disk. Instead, what you would typically do is use a conventional editor, and even one written in Forth, that will edit a source code file and then load it in. Now, in the Figforth model, every block of a source code file is a fixed number of lines of equal length. I believe 16 lines of 64 characters. And so you're just essentially editing this 2D array of characters. And let's see, where is it? Yeah. This arrow symbol right here, that word basically means go to the next page of source code. That says, all right, you're done parsing this page, load the next block of code in and start parsing it.
Wait, while I'm still defining a function?
You can't do that while you're in the middle of a function.
Oh, okay.
You have to have finished a function at that point. But again, with the style that's normally used here, you wouldn't have any function bigger than a page. Now, other implementations use more conventional file structures where it's just, like new line terminated lines. But Fig's approach was to say, we're going to have a very, very simple way of doing it. Yeah.
Do you, we don't have to get into it right now, but do you have any references on, essentially the folks who have written interpreters and things? I'm really curious. I mean, I can see that the overhead from like function calls, like this is obviously a very function call heavy language. They want you to use lots of small
Right.
functions. And I can imagine that the cost of that is relatively low, but
Mhm.
also I'm curious about what kind of elements it needs to keep track of, because there's not a lot of local context, but there's a little bit, and it also needs to know where to go back to
Yes.
in execution. So there must be some sort of shadow stack that's
Well-
being used for the control flow there.
There is. Now, I don't have anything on the slides about it, but these references here to R, those are referring to the return stack.
Okay.
So there's the stack of values, and then there's the return stack, which is the normal hardware stack we would think of. The R's with the arrows let you move back and forth between the two stacks. So in effect, you've got two stacks that I can arbitrarily move things from one side to the other. Now that makes this language very interesting from a theorist's point of view. So if you're not a theorist, go to sleep for a few seconds. We know that a two-stack machine is equivalent to a Turing machine, where each stack represents what's to the left and to the right of the head. So that makes Forth, right out of the gate, without even having to think about it, Turing complete. And that also puts it into that same class of why I like languages like Forth and Lisp, because of course Lisp is built on the lambda calculus that Church put forward to prove the same result that Turing proved when he put forward the Turing machine. And to make things even more interesting, Church published first. Turing is like, what do I do now? One of his correspondents said, oh, you need to publish anyway, yours is different enough and interesting enough, but what you should also do is prove that your two models are equivalent. And so he sticks this little appendix on there that proves they're equivalent, and to this day we consider that capability to be the definition of computable. So to me, something like Forth is a very, it feels good because it is so theoretically sound. I know that's not what most practicing programmers consider to be the value of the language they use, but I'm not typical. Let's see, what else? As long as we are here, I'll mention one that I'm not seeing off the top of my head. You know, they don't have them like in alphabetical order or something. There's one called allot that works like a variable, only you allocate a big chunk of space. Yeah, oh, there it is, right in the middle. That's the problem. It was right in the middle, I couldn't see it. But yes, allot is essentially how you create an array. You're creating a block of space, but instead of just saying allocate a variable, I'm saying allocate this many bytes and give the beginning of it a name.
Is that how you also do structures?
Yes. Now, since it doesn't really have the concept of type the way we're used to, there's really not much difference between a structure and an array. Kind of like in BCP or other typeless languages. All right, so let's see what else we've got. So here are a couple of simple examples, well, 3 simple examples. The first one does the factorial, calculating it iteratively. So let's, rather than watching me type and make use of my backspace key, I'm going to cut and paste it. And what this is going to do is, I'm going to take whatever number you want to find the factorial of, add 1 to it. Then, I'm going to put 1 as the starting point of the loop on the stack. I'll swap those 2 numbers. So, I'll actually be starting from the higher number going down. No, take that back, because I've got swap and then over. So I'm going to have the N1 swap them, and then I have 1, n, and 1 on the stack. Now, that 1 and n are going to be used by the do command to specify the number of iterations of the loop. It starts at the top of the stack, the value that's on the top, and the value that's on the second position of the stack, that's where it stops. So do loop will go up to a point where it's equal to or greater than the top of the stack, or the second element on the stack, and stop. So, in that case, what it's going to do is count from 1 up to, but not including, n plus 1. Each time I'll grab the value, multiply it, and voila, we have factorial. So, take a simple example here. 5 factorial, of course, is 120. 7 factorial, 5,040. 8 factorial. Fourth on small machines is traditionally a 16-bit integer. The value of 8 factorial is greater than 32,768, which is why we see it as a negative number here. I did mention that there are double precision operations for a lot of this, so you could go to a 32-bit value there. The nature of a particular fourth implementation tends to be somewhat tied to the hardware. Yeah.
Is there alternatively an unsigned integer or a way to print it unsigned?
There is. I believe in this one, well, first of all, any non-decimal base will be printed without the sign. Only in base 10 does it ever do the sign. And at least in some fourths, and I don't remember if this one is one of them, there's a variant of the U operations which operate unsigned where you can say U dot,
Okay.
and it would print it out unsigned. I don't remember if this one has that or not. But it's got the U divide and the U multiply for those to do the unsigned multiply and divide. Yeah, that would get you, well, that would get you 8, but then 9 would be a problem. Yeah, factorial is one of those things that doesn't take you very long before you're going to get into trouble no matter how many bits you've got. Okay, so another example is the good old greatest common divisor. This is Euclid's algorithm. And so we're going to do a different type of a loop here. We've got a begin and an until. So it's not going to count an index. Instead, what it's going to do is it's going to repeat the area between the begin and the until whatever's on the top of the stack at the point until is executed is true. When the top of the stack is true, at that point the loop will end. So what we're going to do is we're going to swap the two numbers, do an over, that again gets 2 copies of one of them. That takes the top 2 numbers now that we can take the modulo of. We'll duplicate that value because we're going to need it to test against. If it's 0, then the next one down is the greatest common divisor. The usual form of the way you think about it is I've got 2 numbers, the bigger and the smaller. Find the mod, throw away the bigger one, the smaller one moves down here and the mod moves down there, and you just keep doing these things like that. That's the way we usually think of Euclid's algorithm going, and in this case we're just doing that on the stack by always making sure that the thing on the bottom is the smaller of those 2 that we're doing the mod on. So if I wanted to grab a couple of values here, say 144 and 24, and find the greatest common divisor of those. Turns out I picked 2 numbers that weren't too fun. 24, let's try 144 and 36. That was not fun either. All right. 144 and, well, see, the thing is, if I pick an odd number, like say 5, then I'm going to end up with the greatest common divisor of 1. Because 144's only factors are Well, actually, I could pick something that's a multiple of 3. That would give me something. Because the prime factorization of 144 is just 2s and 3s. Let's see. Now, you may wonder, well, can you do factorial recursively? The answer is yes. How actually varies quite a lot from version to version of Forth. In the case of Figforth, we actually make use of that little thing I mentioned earlier where we suspend the compilation, do something, and then resume compilation. And what we do when we do that is we smudge. Now, what does smudge do? There's a flag in the Figforth implementation on every word that says whether or not this word is visible. While you're in the middle of defining the word, it's set to false so that it's not visible. Smudge toggles that bit. So by doing a smudge in here, then the arfact now becomes visible inside of itself, so I can do a recursive call. But because the end of a definition automatically toggles that bit, I've got to set it back. Otherwise, it will disappear out from under me and I won't be able to use it. So this otherwise is pretty much the usual sort of thing you would expect for a recursive definition. We're going to duplicate again for the same reasons I said we often do that. We're going to test something and we still need the value. If it's 0, of course, then we're going to throw away that saved value and our result is 1. Otherwise, we're going to duplicate the value, subtract 1, do the factorial on the n minus 1, and then multiply them together. And that's our result. I don't think I'll run that one because I've got one more example I want to talk about. It's a little bit more involved. This gives you a little bit better sense of what you would do really writing Forth code and how you would break the problem down. So here the task is we're going to look for all 3-digit numbers that are equal to the sum of the cubes of the digits. It turns out there's 4 such numbers. And somewhere along the line, years ago, I was reading, I think, Kiloblog magazine, and somebody put this problem up as a neat little benchmarking kind of test, really. And for some reason, that problem has always stuck with me. And it's always one of the first things I do in any new language. So we're going to go through this here. All right, so obviously if we're interested in cubing things, we're going to go ahead and define a function for cubing. Nothing terribly surprising there. We're just going to duplicate twice and multiply twice. That's simple enough. There are 2 basic approaches to this problem. One, you can have 3 nested loops generating the digits individually, and then cube them all, and then piece them all together, and then ask is they're equal. Or you can take the numbers, split it out into the 3 digits, and cube those. I'm taking the second approach in this particular implementation, and so I need this function here called digits, whose purpose is to take the digits of a 3-digit number and make them 3 different values on the stack. Well, to get the 3 values, I'm going to duplicate twice. Then what I'm going to do is operate on each one of the 3 and use this rotate operation here, here, and it's not actually necessary here, but for my sanity I kept it there, to cycle the set through. And what am I going to do to each of them? Well, the first one, I'm going to get the hundreds digit by just dividing by 100. Everything is integer, no floating point. This is another good reason to like the language. As I've got to find this quote to make sure that I'm saying it correctly, but I believe it was something along these lines. That Neumann said, if you don't understand your problem well enough to program it in scaled integers, you don't understand your problem well enough to program it. Again, the theorist in me says floating point is really nasty stuff. You got to be really, really careful with it. you know, the usual properties we expect of numbers don't hold in floating point. Associativity doesn't hold in floating point. Anyway, integer division by 100. Modding it with 10 is just going to give me this ones digit, and then dividing by 10 and then modding with 10 is going to give me the tens digit. So this is going to turn it into 3 individual digits. Once I've got those, I'll cube each one of them, again using that rotate to cycle through. And now I can build, now that I've constructed these utilities, I can build a problem I really want to do and say, all right, go from 100 up to, but not including 1,000. Grab the loop counter, turn it into digits, cube them, add them, and then ask, is it equal to I? And if it is, print it out, otherwise keep going. So that's going to be our coding of that. Whoops. It can't quite take it as fast as I was giving it. Oops. There we go. Okay, so while we've been discussing it, has anyone figured out what the 4 numbers are?
There's 4 of them.
There's 4 of them. Well, the first one's 153. Then 370, 371, and 407. And that's checking the other 600 values to find out none of them actually are. You know, you could fairly easily put something in that says, oh, if I've reached a point where any one of the digits is already bigger than the number in question, don't bother. But as you can see, it doesn't take too terribly long here.
What's the clock speed on that?
The clock speed on that is 2 megahertz.
All right.
It's a 6809B. The way it's set up in the hardware is you've got an 8 megahertz signal going in, and it doesn't divide by 4 internally to create a 4-phase operation internally. So it's basically 2 megahertz. And that's not too bad a result for that kind of speed of computer. Let's see. Okay, so I think that's all of the examples that I had to look at. Does anybody have any other questions? Yeah.
Yeah, if I/O isn't memory mapped, is there another way to access I/O devices?
Generally, it would need to be built into the language as something specific to that platform. Normally, what you have available is the console and some form of disk I/O. And the way disk I/O works in the basic Figforth form makes use of, in particular,
3 lines down all the way left.
okay, yeah, the block, that's a block number you're operating on. Buffer is a place that holds it. Now, there's an RW, which I'm not seeing right now, but an operation called R/W that does a read or a write. You push the operations on the stack saying what block number you want to do this with, and then execute that word, and it will read or write based on another value in the stack that's, remember, I think it's 1 for read, 0 for write. And so that gives you disk I/O. Now, obviously it doesn't give you disk I/O by name, it gives it to you by block number. And I don't think I've got it in, I've been experimenting with adding to this version of it yeah, I don't think it's in this one, another command called lookup, that you basically put a string on the stack, and then it gives you back the block number where that file starts. And then that lets you do things by name.
Do you have any blocks that you can show us?
On this one, let me see here.
No, that's fine too.
I can probably, if you come by my table tomorrow or Sunday, I can probably do that. I would have to do a little bit of looking, it would be kind of boring for the next few minutes. Any other questions? Yeah.
Would you just like to comment on the use of create does? Because that was considered one of the more powerful parts of Forth.
Yeah, that's actually connected with the sort of thing I was talking about before, with the idea of being able to create words which have sort of higher level functionality. They're more like keywords in a language. The create, build, does words are all part of that process whereby I can create like a new kind of a loop, for example.
What does do?
What happens is you, I would have to go back and look at the documentation to remember the order, but you have essentially two pieces of code, one that's executed during compile time, and then another that's executed during runtime for that particular word. And then something like a loop, okay, well, the compile time part will set up the loop, reserving an index variable, for example, and then the runtime part will carry out the decision about whether to repeat or not. And if I remember right, I think the does is the part that, yeah, I think the builds introduces the compile time part and the does introduces the runtime part. So yes, you have a little higher level of being able to manipulate the language than you do in most languages, because you can, in effect, create new control structures. And that is pretty unique. There aren't very many languages that let you do that.
Because the novelty that in Forth, I think, is that in many languages, there's this like layer of abstraction between the language specification and then what it does to cause that to come into effect. Forth makes no pretense of hiding the implementation from
That's
you.
right.
To do this other stuff, you're expected to become like really intimate with how dictionary words are created and then machinery.
And in a sense, that goes right back to the original quote that I put up by Moore, that a really good programmer can write brilliant code in Forth. Bad programmers will write even worse code than they normally would in Forth. And there's the old saying, you can write Fortran in any language. Well, if you're working in Forth, Fortran is especially bad. And, Moore's perspective was, I don't really care about helping out bad programmers.
So that actually brings up an interesting point, though, because I think there's a difference between a bad programmer, right, and a good programmer who is fallible, right? And so one of the challenge, I'd be interested in your observations about how effective it is, or how do you effectively debug Forth, because I mean, you can build unit, the equivalent of unit tests, right? You individually test your individual functions. But I could see a situation very easily where you consume one too many elements in the stack in one of your functions, and you don't even know about it until, hundreds of milliseconds later, right? In your execution.
Certainly, like any language, there are potential pitfalls. Now, from a debugging perspective, I generally approach it very much like I do with something like Lisp. I will take each of the utility functions that I'm creating and test them in isolation. Now, if I'm doing so in isolation, starting with an empty stack and that one consumes too many things on the stack, then I'll know. But once I've been able to gain some confidence of it in isolation like that, then I'll use them in combination. And I generally don't find that I'm any more error prone in this language than I am in others.
So it's the basic truth of, we call it unit testing now, but the idea is you test each individual component,
Right.
and you build enough test cases for each one to feel confident
Yep.
that it's not doing something dumb.
And like in this example here, the tendency in the style of the language encourages very, very simple functions.
Right.
So constructing enough test cases to feel confident with those is not all that difficult. unlike, you know, a function where just getting code coverage, it would take, you know, dozens of different input data sets. Functions this simple tend to be a little bit easier to gain that confidence in.
There's a derivative language of Forth called Kitten. It's a statically typed and analyzed version of Forth. So there are people who maybe think that testing isn't sufficient, but I think it hasn't gotten a lot of traction in the community.
Yeah, that one I have not heard of. I've heard of a few other variants of it, but I haven't heard of Kitten.
So probably because it's a concatenative programming language.
But yeah, and that was one of the other big things about Joy is that it's concatenative. You know, that kind of a question always reminds me of the famous quote by Tony Hoare when he said there's basically two ways to create a program. One is to create a program so simple there are obviously no bugs. The other is to create a program so complicated there are no obvious bugs. You know, to a certain extent, I think there's a lot of reality in it. And I think most of us have seen that in our experience. The other thing that I tend to do when somebody looks at a language like this and goes, okay, that's just too weird, I can't touch it, is I like to point out that there's a big difference between the question of how easily can I learn how to do things and how effective can I be once I learn how to do it. What most people call ease of use, they're really saying how easy is it to learn simple things. But I'm not adopting a new language to do simple things. I'm adopting it to do more complex things. I'm really interested in how effective is it for me once I have mastered it. And in that kind of a perspective, I find Forth, like other languages, like Lisp and whatever, to be not any more error-prone or more difficult for me than, say, C. And unlike some of the newer languages that are in vogue these days, these languages are simple enough I can hold them in my head. If I can't hold the whole language in my head, then I can't be very effective using it, because I'm spending half of my time looking something up, which kills my train of thought. So I've begun to adopt this philosophy that a friend of mine suggested, that if the language specification is more than 50 pages, it's too long, too complicated a language. That I would rather have the language be more primitive, but yet be able to hold it all in my head while I'm working, than have a more complicated language. I have to constantly be looking things up. I realize that's not a terribly popular perspective, but that is my perspective, and I will share it with you, and you will get everything you paid for.
So you should do everything in sub-like assembly then?
I frequently do things in this way. Well, in fact, most of the code on that was done in assembly, and then I pulled in the Forth assembly listings into it.
I meant OISC.
Oh,
Just a giant list
yeah,
of moves, one instruction. That's all
that's
you gotta
kind
know.
of. I actually think about that sometimes for fun. There's a variant on that that is kind of the architecture that Turing used in the early thoughts on the pilot ACE, on the ACE that later then became manifested in the pilot ACE. And that is that every instruction just does one thing. It just copies from one address to another address. But some addresses are special. To me, that's such an elegant and beautiful way to design a machine. I don't know why that didn't catch on.
Yeah, that sounds exactly like a transport triggered architecture.
Mm-hmm. Yeah, yeah, it really does lead into the kind of data flow stuff that now is leading in that. And in fact, if you want to see an example of a machine that operates that way, the Bendix G15 we've got in the museum works that way. The guy who did the design for the G15 had also been one of the moving forces behind doing the pilot ACE at the National Physical Laboratory. He was, well, I might as well mention him. Harry Huskey, probably the most influential unknown person in the history of computing. And he is, as far as I can tell, the only one of the original people who's still alive. He turned 101 this year. He was one of the designers on the ENIAC, was part of the development process for the EDVAC before he went on sabbatical to the National Physical Laboratory in England, where he influenced work on the ACE, came back to the US, he developed the SWAC, the Standards Western Automatic Computer, then designed the G15 for Bendix, joined the faculty at Berkeley. One of his PhD students at Berkeley was Nicholas Wirth, who went on to do Pascal and Modula and Oberon. And one of his master's students was Ken Thompson, who went on to do B and Unix and Go and so on. So yeah, he's definitely one worth looking up and finding out more about. Harry Huskey.
How do you spell his name?
Huskey. No, Key. Yeah, Huskey. And like I said, at least the last time I looked on Wikipedia, he was still among us. And everyone else who worked on the ENIAC project, as far as I know, is gone. So, any other questions? Going once?
Do you have any? So I could easily see this being sort of difficult to maintain. Do you have any tips for, or like, I know there's standardized ways of writing comments, right? But
Yes. Well, for example, it's typical in the documentation of something to, a lot of times the way it'll be done in a lot of code is you'll have the colon, the name, and then you'll have a descriptive comment out to the side. Then you'll have the next line be the executable of that new name. And the comment out to the side typically is organized in a way where the beginning of it tells you what it expects to find on the stack and what it leaves on the stack. And then any additional descriptive information that's necessary. I know that in my own programming, when I'm going back to something that is generally a fairly low-level kind of thing, it's that what am I expecting to see in the environment that is the thing I'm most likely to have forgotten. And I've had a little opportunity to revisit some of that recently, in fact, because remember at the very beginning I said I wrote a Forth compiler because we didn't have one at my college. Well, a few years later I ended up using that as a user environment for a little operating system I did for my senior project. Well, when deciding to do this and make Forth my exhibit this year, I set out to try to resurrect that old code. And it's a real experience seeing something that you last saw running 35 years ago suddenly start running again. And yeah, there were several bits of that code, which was all in assembly language, that were kind of like, okay, I remember this part. I don't remember what I was doing here. Unfortunately, I don't have it fully functioning and ported to real hardware, but it pretty much works on SimH. And I'll show you if you're interested at my table this weekend.
Can you comment on Forth assembles? So assembles written in Forth, because that was for me the eye-opener.
Yeah, it's an interesting approach. A lot of people will want to be able to integrate assembly language into their Forth code. And so there are a lot of Forth environments that have an assembler built into them, and usually that assembler then is in turn written in Forth, which makes it a really interesting kind of layering, because the core of the Forth implementation is usually written in assembly language. Then you've got an assembler written in Forth, and then you're kind of combining the two in the code.
But it's also unbelievably short.
Yeah, it is an extremely small language in terms of size. I mean, when you think about it, each one of those things there is only taking up one address.
There's a wonderful implementation called Jones Forth. If you look on GitHub, you'll find a couple versions of it, but it's a really well-commented Forth implementation that starts at the very, very basic core of the interpreter and builds on it. And
Oh yeah, that's the self-bootstrapping?
Yeah,
one.
it's really, if you're into that thing at all, it's just a joy to read.
Yeah, that sounds like a good one to study. I'll have to take a look at it.
Has anyone here heard of At-Last? At-Last. Autodeck threaded language. The founder of Autodeck has a website. Google Atlas will come up with, and he has a version that runs in the Raspberry Pi. But Atlas was put into Autodeck products to make them programmable, which is their major characteristic. So AutoCAD has 4 built into it.
Cool.
Now, Lisp, you mentioned Lisp, they started off with tiny Lisp.
Okay, yeah, because I knew they had.
And dropped it. And get the document written by the founder of Autodeck. He explains why Forth. It's one of the best explanations I've ever read. Why Forth.
That does sound like a good read.
So it's a good read.
So you all have some good recommendations for reading. I will also go out and try to read this.
I'll have that document. I have that document. Bring it in and put it on your tape.
That'd be great. All right, well, if there's no other questions, I think we're basically out of time and then a little bit. So thank you.